Welcome again in the course module of communication engineering. So in the last lecture, we were started the topic pulse code modulation, and we have already seen what are the different line codes that we are generally used for the encoded binary bits. So in the today's lecture, we have to see what will be the requirement of the pulse code modulation, such as bit rate and bandwidth requirement of the PCM system. So that we have to look at in this particular lecture. So let's start the discussion. So how to calculate the bit rate requirement and bandwidth of the pulse coded modulation system. So in the last lecture, I told you about this transmitter part of the pulse code modulation system, in which what we have seen is our first block should be a source of continuous time message signal. And then a message signal has to be generated, which will be in the analog form. And then it has to be passed through a low pass filter first, okay, to band limit the frequency component of the message signal. And then based on the maximum frequency component in the message signal, this signal has to be sampled at a particular sampling frequency. After sampling, the sampled value has to be quantized to a particular quantization levels, and then this quantized value has to be encoded by using the binary bits. Now, this encoded bits, I told you that in the case of pulse code modulation, this encoded bit has to be used for generation of the line codes, and generally for transmission of the pulse code modulated signal, we prefer the binary bipolar signaling. Okay, so we prefer the bipolar signaling that we have already discussed in the previous lecture. So I told you that the bipolar signaling could be of return to zero type, or it can be also non-return to zero type. So basically, we need to launch a particular pulses, okay, electrical pulses based on the particular code bit, okay, binary data. So based on those binary data, we need to generate a electrical pulses, okay. So in the previous lecture, I told you that in the case of bipolar signaling, how this signaling was defined. If we have taken this particular binary data, let us say this is our binary data, 0 1 1 0 1 0 0 0 and 1 1, then this has to be represented like this. Whenever there is a 0, there should be no pulses, and whenever there is a 1, a positive pulse is to be transmitted, and whenever there is a next binary bit equals to 1, a negative pulses will be transmitted. Okay, so alternatively, what we have to do is for binary bit equals to 1, we have to alternately send one time a positive pulse and the next time a negative pulse. Okay, then again when another one is occurring at this particular point, again we have to send the positive pulses. Okay, and for all these zero binary bit, there should be no pulse transmitted. So this way we are actually transmitting the various pulses, okay, in the case of bipolar signaling. So in this particular case, I have taken for non-return to zero case, okay, because the pulses that I have shown in this particular picture is actually being transmitted for the entire bit duration TB. So now we have to discuss about how to calculate first the bandwidth requirement. Okay, so you please try to see this particular pulses. Okay, what we can see is everywhere we are going to get a certain rectangular pulse. Okay, everywhere we are going to get a certain rectangular pulse of certain width. So here again we are having a certain rectangular pulse. Again at this point we are having a certain rectangular pulse. Okay, again here we are having a certain rectangular pulse. Okay, though its magnitude is negative, but it is a rectangular pulse. Okay, so basically while transmitting the signal by using the bipolar signaling, whether it is a non-return to zero or a return to zero case, always this pulses will be a rectangular pulse. Okay, so basically because of its nature, we have to study about the rectangular pulse, and then we have to talk about what will be the bandwidth requirement for this particular rectangular pulses. So now let's suppose that we have any signal xt, okay, which is a rectangular pulse, which is defined in this particular graph, okay, in this particular picture. So this rectangular pulse is actually being defined in a time between minus t1 to t1, okay. It means that for this duration, it is having its amplitude equals to unity. For this particular case, I have taken this magnitude equals to unity while transmitting the pulse coded signal, okay. This magnitude may not be unity, okay. It can be anything else. It can be 5 volt, it can be 2.5 volt, it can be 6 volt, whatever it is, based on the way we want to send the pulses, okay. So here for the simplicity, I have taken it to be equals to unity. So now xt is equals to 1, okay. We can see that we can define it mathematically as xt equals to 1 when mod t is less than t1. So whenever mod t is greater than t1, this xt is going to be 0. So here we can see that this xt is going to be 0. Now, if we see this particular pulse, in this pulse, the width of this pulse you can calculate is equals to 2t1. Okay, we can see that the width of this pulse is equals to 2t1, and its magnitude in this region is equals to unity. So if you want to get the information regarding the frequency component of this particular pulse, I would like to tell you that whenever there is a steep increase, okay, because before minus t1, the signal value was equals to 0, and certainly within no time, this signal is actually reaching to a certain finite value equals to 1. So whenever there is a change occurs in a signal within a 0 time, obviously the bandwidth requirement for such signal would be infinity, okay. But for our practical cases, we have to do a little bit, we have to done some workout, okay. We have to work out here a little bit to get more information. You remember that for such signals, the ideal bandwidth requirement would be infinity. Why it is infinity? Because within no time, the signal is actually changing from a value 0 to 1, okay. So it should not be like this, okay. It should not be like this, because even in the practical cases, we cannot generate a pure rectangular pulse of this kind, okay, of this kind, because there will be a certain transition time will always be there. Like it may be in the like picoseconds or nanoseconds, it may be a very small time, but obviously any signal which is varying from 0 to means which is changing its amplitude from 0 to 1 or 0 to any other value, it will take a finite amount of time, okay. It will take a finite amount of time to change from 0 to 1, okay. It doesn't mean that it can go directly from 0 to 1 within no time. So okay, so this is just for your theoretical consideration. So let us suppose if we want to calculate the Fourier transform of this particular pulse, okay. We have already defined the expression for the Fourier transform. So if we have any signal xt, okay, in the time domain, its equivalent Fourier transform x omega can be defined as equals to minus infinity to infinity xt e to the power minus j omega t dt. So now here we can substitute the limits, because this signal is actually available in between minus t1 to t1. Okay, so this limit can be transformed into minus t1 to t1, and then you can substitute x equals to unity, and then you can solve this particular equation. So after doing this simplification, you will be getting this expression equals to 2 sine omega t1 divided by omega. Now I am just modifying this expression a little bit. So if we multiply t1 here, and if we divide, means multiply t1 in the in numerator, and we can also divide the t1. So t1 will be cancelled out. So here we can have this 2t1, okay, and this another t1 can be in the denominator term. So now basically the sinc function, sinc x is actually defined like sine pi x upon pi x. So we can also represent the same expression in the form of sinc, so that you can write like x omega, that can be written as 2t1, and sinc of omega t1 divided by pi. So obviously if we write sinc omega t1 by divided by pi, if you express this sinc function in this form sine pi x by pi x, okay, then obviously here x is equals to nothing but our omega t1 pi. So this will be your omega t1 pi multiplied with the pi, and again omega t1 by pi multiplied with the pi. So pi will be cancelled out, and ultimately we are going to get sine omega t1 divided by omega t1. So this is the actual representation of the sinc function. Okay, so basically the Fourier transform for a rectangular pulses, okay, in the time domain, okay, the Fourier transform of the rectangular pulse will be a sinc function, okay, will be a sinc function, or it can be further written as 2t1 equals to sine omega t1 divided by omega t1. Now, what we can do is we can do a certain analysis, okay, whenever this omega t1 is tends to 0, okay, obviously we are just substituting omega tends to 0, then obviously sine omega t1 divided by omega t1 will be equals to unity, and that time the magnitude will that we are going to get is equals to 2t1. So this is what our magnitude is, okay, here we are getting the magnitude equals to 2t1, and now we can calculate at what values of the omega this function is going to be 0. So obviously here we can see that whenever omega is equals to like if we substitute pi upon t1, then t1 and t1 will be cancelled out, and here we are going to get the sine pi. So sine pi will be 0. So we know that whenever sine is pi, 2 pi, 3 pi, 4 pi, or so on, okay, any integer multiple of pi, at that time this function is going to be 0. So that we can also evident from this particular picture. What we can see here is first we are getting the maximum value at 2t1, and then at first at pi divided by t1, this function is going to be 0. Then again at 2 pi t1, this function is becoming 0. Again at this point 3 pi upon t1, this function is becoming 0. And here we can see that because this function is inversely proportional to value of omega, it means that when the frequency omega is increasing, the magnitude of this function is going to be reduced, okay. So that we can also see from this picture that this particular waveform, which is the sinc function, okay, is having its peak magnitude when omega is equals to 0, and after that the magnitude of this function is decreasing rapidly. It is decreasing rapidly, but you remember that this function will go up to infinity. Omega will go up to infinity, okay, and that time this function will go will become 0, okay. So basically even from this graph what we can see is ideally the bandwidth requirement, because it is in the like frequency domain, okay, here omega we have taken, so this axis is on the radians, okay. So even in this particular graph itself we can see that the ideal bandwidth requirement for this sinc function would be infinity, okay, would be infinity, because we have to consider the entire band, okay, and therefore the bandwidth requirement would be infinity. But for most of the practical cases what we can find is that as I explained even in my previous lectures, that this is called as the major lobe, okay, is this called as the major lobe, and all these other lobes are the minor lobes, okay. So basically most of the power content of the signal is actually lies within this major lobe, okay, and all other side bands, all other minor lobes are containing only very small amount of power, and therefore these side lobes can be neglected, okay, can be neglected. So for the approximated bandwidth, what we can say that the width of the major lobe is can be considered as the bandwidth of this particular rectangular pulse. You remember that it is just for the practical cases, okay, just for the practical cases. Ideally it should have the infinite bandwidth, but for the practical cases the bandwidth of this rectangular pulse can be considered as the bandwidth of our first bandwidth of our major lobe, okay, major lobe. So this is our major lobe. So this lobe which is having its bandwidth equals to pi t1, okay, so this pi t1 can be considered as our bandwidth of this particular uh, uh, Fourier transform x omega, or this sinc function, okay, when we are neglecting all the higher order frequency components, okay, these all higher order frequency component is being neglected while calculating the bandwidth of this particular sinc function. So you remember that for most of the practical cases we can consider that the bandwidth of this sinc function, or you can say the approximated bandwidth, okay, you can say that the approximated bandwidth of this sinc function that we get is that value is equals to pi upon t1 radians, okay. So if you want to calculate the same thing in hertz, then obviously it has to be divided by 2 pi. So once you divide this by 2 pi, you will be getting this bandwidth equals to 1 upon 2t1 hertz, okay. So this bandwidth will be equals to 1 upon 2t1, because we are dividing this because this is in the radians. So we have to divide it by the 2 pi. So you will be getting this bandwidth in hertz equals to 1 upon 2 T1. So what we can see is that the bandwidth, approximated bandwidth of the rectangular pulse is actually can be calculated by having the knowledge of its width of the pulse. So basically this 2T1 is nothing but the width of the this rectangular pulse. Okay, so what I can write is the bandwidth is also equals to 1 upon pulse width. Okay, whatever be the pulse width, that can be so inverse of that will give the approximated bandwidth of the our rectangular pulse. Now here we can see that if we apply the same concept, okay, if we apply the same concept to this particular signaling scheme, okay, so when we are sending any pulses, let us suppose we are sending this particular pulse, then at this moment what we can see that what is the width of this pulse. So here we can see that this is 3 TB, this is 4 TB, and this is 5 TB. So each bit is actually each pulses is actually being generated for the duration of TB. Okay, duration of TB, which we are referred as the bit duration. Okay, so if the width of this is equals to TB, then the bandwidth for this binary bipolar signaling will be equals to 1 upon TB. You remember that this is the case for the NRZ, non-return to zero case, which is this case. Okay, whenever if we consider the return to zero case, you must be aware that the pulse will be generated for half of the bit duration. Okay, so it will be generated for TB by 2 duration. Okay, TB by 2 seconds duration. Okay, and that time this width will become half. So at that time, the bandwidth requirement for this type of pulses will become 2 upon TB for return to zero cases. So if it is not specifically mentioned, you can calculate the bandwidth requirement considering that the signal is a bipolar signaling. Okay, the line coding is used as a bipolar signaling, non-return to zero case. And if it is mentioned that it is a return to zero, or if it is something else, then accordingly you have to crack your problems. Okay, you have to solve your problems. So now you try to understand how to calculate the bit rate requirement for the pulse code modulation. And we have already seen what will be the bandwidth requirement of the pulse coded modulation. So you try to see how to calculate the bit rate of the pulse code modulation system. So let us suppose that as we already seen in this previous case, that first we have to do the sampling, and then we have to quantize the signal, and then we have to encode the signal. So basically what we are doing is first we need to have a particular sampling frequency. Okay, that will be following the Nyquist theorem. Okay, so as per the Nyquist theorem, the sampling frequency fs should be greater than equals to twice of the maximum frequency component in the massive signal. Okay, so you remember that if the massive signal is a multi-tone signal, we have to talk about the maximum frequency component. Okay, so the sampling frequency should be greater than or equals to the maximum frequency, twice of the maximum signal frequency. Okay, so now this is sampled signal. So since sampling frequency, let us say it is fs, and let us say there are such L quantized levels. Okay, we have to talk about how many quantization level we have. So let us suppose that the dynamic range of the signal is such that we have the L quantized levels. Okay, so how this quantized level we are defining is, so first what we are considering is, let a massive signal is band limited to FM. Okay, and is sampled with the sampling frequency fs. Okay, and then it is having a L quantization levels. Okay, so what we mean to say the L quantization levels, so if the quantized level has to be encoded by using the binary bits, then this L should be equals to 2 to the power n. So what is this n represents? So n represents the number of bits required for encoding encoding per samples. Okay, number of bits required for encoding per samples. Okay, to encode the samples. Okay, so basically what we are doing is, if we are having suppose if we are having L equals to 8, obviously the number of bits that will be required is equals to 3. Similarly, if we have L equals to 15 or 16, then n should be equals to 4. Okay, remember, if our L is equals to 20, suppose that if L equals to 20, then what should be the value of n? So n equals to 4 can only have the quantization level is equals to 16. Okay, but if we want more than that, then the number of bits requirement should be greater than 4. Okay, it should be greater than 4. That you have to remember. So it is not required that the L should be equals to 32. Okay, because 2 to the power 5 will give you 32 levels. Okay, but even if you want only just to have the 20 finite quantized levels, at that time the n should be equals to 5, because n equals to 4 cannot accommodate uh, 20 levels. Okay, so this way we have to define the quantization levels. Okay, now you try to recall that what we are performing is, first we are sampling the signal. Okay, first we are taking the sample of the analog signal, and that sample value should be quantized. Okay, so at what rate we are taking the samples? We are taking at the rate of fs. Okay, it means that if suppose that if fs is equals to something like 8 kilohertz. Okay, 8 kilohertz. So generally in the commercial pulse coded modulation system, PCM systems, you will find that for transmission of these speech signals, because the speech signal is containing its frequencies up to equals to 3.1 kilohertz or 3.2 kilohertz. Okay, so we can band limit the frequency component within the 3.5 kilohertz. Okay, so generally what we perform is, what we do is we are taking the oversampled signal. If you remember that in my discussion, okay, of sampling, okay, if you remember, we have to oversample the signal. Okay, we are not doing the strict sampling at which the sampling frequency is exactly equals to twice of the maximum frequency component, but we have to take the fs that should be greater than twice of the maximum signal frequency. So basically, because the maximum frequency component in the massive signal in the case of human voice is around 3.3 kilohertz or 3.5 kilohertz. Okay, we generally perform the oversampling by choosing the sampling frequency equals to 8 kilohertz. So what does it mean by having 8 kilohertz sampling frequency? The meaning is that we are taking 8,000 samples per second. Okay, it means that we are taking 8,000 samples per second from the given speech signal. Okay, this is the meaning of our sampling frequency fs. So now if we know what is the how many samples we take each second, okay, then we have to talk about how many bits should be there to encode the each samples. Okay, so first we are sampling it and then we are quantizing it. Okay, so we have to encode the quantized signal. Okay, so whatever be the quantized signal, that has to be encoded in a certain number of bits. So that number of bits will be depending on the number of quantization level L that is related to this particular equation. So let us say that each sample, in this case I have taken n equals to 10. You can see that how many bits we have taken: 1 2 3 4 5 6 7 8 9 10. Okay, so total 10. So how many such levels we can define? We can define 2 to the power 10 such levels we can define. So basically you can calculate 2 to the power 10, you will be getting 1024 such quantized levels that we can have. Okay, so basically each sample, okay, each sample, okay, that we have sampled at a Nyquist frequency at a certain sampling frequency should be quantized first, and then it will be encoded by having the total number of bits equals to 10. Okay, in this particular case. So now once we perform the encoding, okay, then you can see that by using the bipolar signaling, we will be having this type of particular uh, signal. Okay, we are going to generate this type of line codes. Okay, this type of line codes. So now what we can see is particularly after generating this line codes, we can see that because this line code is corresponding to only one particular sample. Okay, this is corresponding to one particular sample. So basically this entire pulses has to be sent just within the ts second. You remember that the total duration of this particular all the pulses that we are going to send, that has to be sent within the ts second, because after the ts second, second sample will come. Okay, So again, we are going to get a line code corresponding to the next sample. Okay, so this particular sample or this particular line code is actually representing only one sample. Okay, which is consist of 10 bits. Okay, and that has to be sent within the TS second. Okay, at the next TS second, we will be getting a next sample that is actually quantized, and then again it will be having a certain line codes, and that has to be sent, okay, at the next TS second. So now what we can see is that within this TS second, we are actually sending this 10 bits. Okay, we are actually sending this 10 bits. So how to calculate the bit duration? Okay, how to calculate the bit duration? So let us suppose if we are just sending n bits, okay, by having, I'm just not writing this number like n equals to 10. If suppose that if we generalized it, let us suppose that if we are sending n number of bits within the TS seconds, then what will be the bit duration? Okay, what will be the bit duration TB? So that bit duration TB can be calculated by following this relation. This TS has to be divided by the number of bits n. Okay, this TS has to be divided by number of bits n, because within this TS second we have to send the each pulses. So therefore this bit duration will be equals to TS upon n. Now once we send this many of bits per sample, then we have to talk about per unit time how many bits we are sending through the channel. Okay, how many bits we are sending per unit time through the channel. So how to calculate how many bits we are sending through the channel per unit time? So that is giving us the bit rate. Okay, that will be giving us the bit rate. Okay, so what is this bit rate indicates? It is the number of bits transmitted per second. Okay, that we are transmitting per second. So first of all, once we will be able to, if we are able to calculate how many bits per second we are generating, obviously the same number of bits we are going to send also. So number of bits generated per second, if we want to calculate, how to calculate the number of bits generated per second, the number of bit used to encode each sample. First of all, how many means bits we are using for each sample, and how many such samples are generated per second. Okay, so basically it is the multiplication of the two. So number of bits used to encode each sample, it means that bits per sample. Okay, bits per sample multiplied with the samples per unit time. Okay, the samples which is actually generated per unit time. So obviously the number of bits used to encode each sample is n, small n, and the number of samples generated per second is nothing but our sampling frequency fs. Okay, because I told you that if it is 8 kilohertz, it means that we are actually generating the 8,000 samples per second. So therefore it will be represented by the sampling frequency fs. So basically what is this bit rate? This bit rate can be equals to number of means bits per sample multiplied with the sampling frequency fs. Okay, so ultimately we can also write this as equals to n upon ts. Okay, because 1 upon ts is giving you sampling frequency, and here ts giving you the sampling interval. Okay, so this n upon ts you can see from this expression. So here we are getting ts upon n. So basically this represents 1 upon tb. Okay, so whatever be the means bit duration, okay, inverse of the bit duration is going to give us the bit rate. Okay, so this many bits per second we are actually sending through the channel. Okay, now a similar case we can also calculate what will be the bandwidth. Again the bandwidth requirement will be same as the bit rate. The only thing is that here we have to represent the data in the form of bits per second. Okay, or kilobits per second. Here it has to be represented in the hertz. Okay, 1 upon tb. So you remember that bandwidth, the way we have calculated is the approximated bandwidth. Okay, it is not the actual bandwidth. The ideal bandwidth should be infinity. So I hope you must be able to follow how to calculate this particular bit rate of the PCM system. You remember that sometimes for the synchronization purpose, we do add certain extra bits. Okay, we do add certain extra bits. Okay, at the end of the sampling time. Okay, so that will be called as a frame. So whenever there is an extra bit, if any problem, if it is mentioned that there are certain extra bit is also added for the synchronization purpose, then you have to calculate the bit duration accordingly as per the given question. So I hope you must be able to follow this lecture. If you have any query, let me know by your comment. So please stay connected with the channel. For more updates, I will be coming up with the next lecture. Our next topic will be, we have to calculate the signal to quantization noise ratio for the case of pulse coded modulation system, for PCM system. We have to calculate the signal to quantization noise ratio. So for that purpose, I will be first discussing about the a little bit random signals, because for discussion of the signal to quantization noise ratio, the discussion of the random signal is required. So please stay connected with the channel. In the next lecture, I will be discussing the random signals followed by the signal to quantization noise ratio required for the pulse coded modulation system. So thank you for watching this video. Please stay connected with the channel for more updates.